everything we do here with the actuators, it's all hydraulics. So you'll see the pumps. We have some huge hydraulic pumps. It runs at either 3,000 or 5,000 PSI, up to 10,000 gallons per minute. So we got a lot of flow, a lot of oil moving around. But we take these big servo valve controlled actuators and we hang them off that wall horizontally, and we're able to hook them into those piles or whatever it is we put into the ground. Again, this is about a 40-foot deep pit. We bring an excavator in and we dig it out and put whatever kind of soil we want. In this case, we put in this large riprap because that's pretty much what's underneath there at the Port of Los Angeles. And then they've shipped us these piles and we put them into the ground exactly how they would have done it there. And then they're not here, but they're actually kept on campus, but then the actuators cantilever off that big block and hook straight up into those piles, and then we break them. So you can see where we basically push those piles to a point where you form a hinge at the joint of the pile to the cap. So if you look real closely, you can see some of the exposed rebar, and you can see how the concrete is spalled and broken away, because at that point in time, instead of it just being a stiff structure, it started doing this, and that's where we really start to get a lot of our data on how it's going to react in an earthquake. We put a lot of energy into that structure. So the wires you see hanging out, that's how we record what's happening with the rebar and the concrete and stuff like that. We're looking at the stresses and the strains of the rebar and making sure that it matches our calculations. So the strain gauges we apply directly onto the bar, and they're embedded in the concrete, and we apply a lot of them. I think these particular ones have probably 200 strain gauges in it at different locations of the rebar, along the spiral, the longitudinal bar system, so we can look at it. Same with that building that you guys are looking at. There's a bunch of strain gauges inside that thing, like at the beam to column connections. We've got some bars in there that are kind of special bars, that they're not your standard 60 grade rebar. They're actually 110 grade, so they're high strength rebar. Also some special joint connections and stuff made by DSI. So again, we have a lot of sensors on that big building you see us putting up. The footing of this building is sitting right on top of the shake table. So pretty much the entire top of the shake table is the same dimensions as this footprint. It's 40 feet long by 25 feet wide. It's a large steel platen, if you want to call it that, with a whole bunch of webbing, and there's concrete inside. You'll really see the thickness and how big the table is once we get underneath. It's huge. By looking at it up here, all you really see is a building, but once we get downstairs, you'll understand what's going on underneath. Right now, the table only moves in one direction longitudinally, so it moves this way, which is good. We can still look at earthquakes and stuff like that. Ultimately, the table's been designed to be able to have a vertical and a lateral, which would give us a 6 degree of freedom table. So you'd have X, Y, and Z, and then yaw, pitch, and roll, which is what a real earthquake would represent. However, that's about another $20 million to upgrade, so we're slowly kind of doing it as we go. So right now, that's why we only have the 1 degree of freedom. On campus, we do have another table that does do 6 degree of freedom. It's indoors. We have a ceiling limit, so here we have a lot more, as you can see, versatility with what we build. And we just got to make sure we don't go too high and piss off the Marines at Miramar and mess up their flight path. Other than that, we're okay. What else? You can see, I don't know if you can see them too well. You see all the little plugs in the concrete right here, and it's also in the steel platen on the shake table. They're about 3-inch diameter holes that are spaced at 2 feet on center throughout the whole shake table and throughout all of the reaction mass. And what that is for is so that we can fix these structures to the table or to the mat. So those plugs open up, and you can kind of see, if you look, it's kind of hard to see, but if you look at the top of the footing of that beam, you see some large thread rods sticking up out of that beam. They've got some plastic on it, but you can see that there's a nut and some thread rods sticking up. Those actually screw, those rods screw into a coupler or go all the way through the table, and we plate nut it. and then we stick a jack on that bar, and we pull the bar, and then we tighten down the nut. So we pre-tension those, or we post-tension those bars to get that clamping effect of whatever structure we want to attach to the table or the reaction mats. Sometimes it's necessary to attach things to the reaction mats because we want our sensors to be able to record the sway or the movement of the building, but we need a fixed location to record it from, right? So we'll post-tension one of these frames to the mast so that we can set up a bunch of string pots or sensors that attach to the structure. Like this building, we don't actually have staff on site that construct it. We would, like any other entity, we'd subcontract it out. We design the building or whatever structure it is, and then we put it out for bid, and then, you know, Turner or Morley or Noel or whoever local construction that can do this, we put it out for bid, and we go sometimes the cheapest, but not always the cheapest, whoever gives us the most confidence that it'll be done right. It's a whole different animal doing structures that are science experiments versus actually building the structure, because, you know, we want everything to be like we designed it. You know, we want stuff to be in really, really tight tolerances because we're comparing it to to the theoretical. We're doing the numbers, we're doing the calculations, we've got the theory down, and now we're taking it and we're applying it practically. So the closer we are to how we're designing it, the better. Hence the strain gauges and testing and stuff like that. So we're able to get data, which is an interesting thing because, you know, you go out into the real world and you're building something and it's all about money and time. You know, for us it's all about precision. So, you know, it can be a chore to get something up, you know, when you can just throw a couple extra pieces of rebar in out in the real world, but here it's like, I want that spacing at 4 inches and it's got to be exactly what I called out. So, design and what they're doing nowadays with like trying to minimize damage to a structure is what we're going to do is those were there for the building from any movement below it. So it's like you have a building and it's on some bearings, and you get an earthquake and it starts shaking. Well, those bearings prevent the building from shaking with the earthquake. So we're going to actually have bearings underneath this thing. So it's going to be a several part test. We're going to get the bearings underneath it, which is going to be a huge deal. Imagine jacking up this 1.5 million pound structure and then switching out those pedestals with the bearing, and then it's going to be just floating there. We're going to test it. Hopefully it goes back to zero where it originally started. We put it back in the pedestals and then we clamp everything down with those feeding forces. So it's pretty interesting. What we've got going on is basically this. We've got two pumps. So we've got these servo valves that are kind of like these really fine-tuned valves that give us very precise movement of the table. So they allow oil to flow or prevent oil to flow. So obviously it's got a slide on something. So this main actuator right here is what pushes it. There's one on the other side. The program, this one's pushing down. So that's what gives the table its longitudinal motion. You can see on the side they look like engine blocks. On both sides, those are our servo valves. It's a 7-stage servo valve. That's how we get that precise control and movement of the table. You can see they have their own separate hydraulic supply. I was talking about main pressure, 10,000 GPM. You can see where the fixed pipes go straight into that manifold, which goes straight to the main cylinder, which obviously has the main rod. The oil goes in there behind the rod. All right, real quick, guys. This is what we call our blast simulator. Same concept kind of as the actuators you saw downstairs. Much smaller, different valves. There's a series of poppet valves. They're much different than a servo valve, only because they just let oil flow or they don't let oil flow. And there's a whole bunch of series of chambers with nitrogen. To make a long story short, the design is so that we can throw that piston out at really high velocity. So these actuators you're looking at right here are 25 meters per second max actuators, and then we have some bigger ones that are actually 50 meters per second. To the piston, they slide on those rails, And when we program, we have a series of actuators. They're all programmed together so that they go at the same time, and then we're able to apply that distributed load to the structure. Replicate the shock wave, right? You have to cover a whole surface area. This is the story. This thing is dynamic. It's fast. It happens quick. We're talking milliseconds. That's why we have high-speed cameras. I mean, it blows, literally destroys things. You see those columns right there? It did that to those columns in a matter of a millisecond. Same with these here. A lot of this is for, like I said, Department of Defense. It's blast mitigation. It's to make a structure stronger so you can mitigate blast damage.